Thank you very much, David and Mike, for those introductions. So thank you, and thank you everyone for coming to these 2 days of talks, all about the generation time for COVID-19. So I'd like to introduce our first speaker for this, this first session, Professor Julia Gogg from the University of Cambridge. So you all have heard David mention the JUNIPER Consortium, which stands for Joint Universities Pandemic and Epidemiological Research. And Julia is one of the co-founders of the JUNIPER Consortium, along with Matt Keeling. And I'm going to be talking a little bit more about the JUNIPER Consortium tomorrow, but I'll put a link in the chat for people if they want to find out a bit more in advance. So Julia is a member of both the Scientific Pandemic for Influenza Group on Modelling and also the Scientific Advisory Group for Emergencies. So both of these groups are heavily, do all the advice for the government on the COVID-19 response in the UK. So this event was actually Julia's brainchild, and so she is going to kick us off with for these 2 days of talks by giving us an overview of what the generation time is and why it's important, and I guess really as well why it's a potential topic of interest for the 3 different communities which we're hoping are going to get sort of interacting over these few days. So that's the within host modelers, the environmental modelers, and the epidemiologists. So with that, Julia, I'll hand over to you.
Kira, thank you very much for the introduction. Hopefully you can see my screen, and I'm hoping someone will yell if that's not true, or ping me a message. And I've just done something awful with my screen. Let me move it and then move that away. And now I can also see my screen, which is fantastic. So I'm very excited about this meeting, and hopefully you'll understand why at the end of this intro. It's listed as overview, which is really too grand. I mean, I can't give an overview of all of these areas. And indeed, that's part of the fun of this, is that none of us are experts in all of the areas which intersect here, but we've all got some expertise in different bits of it. So bringing it together is going to be the magic. And having seen the list of participants listening to this now, I think we're set for an exciting event if we can talk together on these topics. So maybe not so much overview as setting the scene, or perhaps even more alternatively, the warm-up act. I'm just going to give you an idea of some of the areas that I think are going to be important in this. So the straw man, or rather the straw model, is the classic SAR, and I don't need to introduce this properly to anyone here. But the things, well, every model's an approximation, right? But things in this that are particularly approximation that we're going to throw out and really take apart and put back together is firstly the mass action of the transmission. Susceptibles, infected, just mix, and that's it. The constant recovery rate. Okay, so you're infected and then just it's a differential equation, so you go out at rate nu. If you take that at an individual level, that's saying you're just in the I category for an exponentially distributed amount of time or some sort of exponential weight. And the other bit that's not obvious when you look at this, but it's the process of when you're infected, you're an S 1 second and you're an I the next second. So there's all kinds of things buried in our simplest models. I mean, the 2 processes are simplified, but just the whole language of it, the SI, etc., has a world built in that we need to start to unpick. So what I'm going to talk about here is what is the generation time? Why should we even care? And what forces shape the generation time? What is the generation time is the easiest one of these. It's definitions. So we've got 2 people here. We've got red person, we've got blue person. And we suppose that the red person infects the blue person. This is a time axis for each person, sort of running in parallel. At this point, red person is infected by someone else we're not plotting here. And then symptoms start at some point later. You've got this period between infection and symptoms starting. Red person infects blue at this point, so maybe you can think of another little arrow popping in here to show the infection happening. Blue person infected from here, and symptoms start for blue person here. Of course, it's possible that symptoms don't start at all. It can be asymptomatic. This is all badly redrawn from this fabulous paper here. Now, this is only here just to give the definitions. Generation time. is from the moment of infection of the first person to the second person. So generation time is defined between a pair of people that you believe to be an infector and an infectee. And it's that time interval. The closely allied interval is the serial interval, which is usually defined as symptom start to symptom start. Now, you can probably see already these are not quite the same thing because the time between infection starting and symptom starting isn't always the same. You might say they ought to have the same mean, and maybe they do, but they certainly don't have the same distribution. For example, serial interval can be negative, right? So you can have this person maybe doesn't show symptoms until ages later, but they're infectious here. So the symptoms could start in the wrong order, whereas generation time has to be causal, has to be forward in time. So they're not the same distribution. One thing I ran the beginning of this talk past my partner last night, who's not an epi modeler, I should say. And his first comment was, "Oh my goodness, you've got the damn stick men out again." And his second comment, which just left me stumped overnight, was, "What do you mean by moment of infection?" You know, modeling wise, it's the moment you go from S to I, or within hosts, it's when you start the timer of when the infection starts, whether your timer usually letter A or tau or C. But what do we really mean physically? Is it the moment the virion goes into the other person or infects a cell? And, you know, is it a virion or the one that causes the subsequent infection? So I've realized moment of infection is indeed ambiguous itself already. Marvelous, nothing simple here. Anyway, that's the definition of generation time. Why should we care? So lots of reasons, but I'm going to pick out a few in particular that have been certainly on our minds with policy needs. There's a lot on this, but this is an absolutely wonderful figure from Emma Davis's paper. So perhaps the best place to focus here is this box here on the top right. So you've got an untraced case, you've got person A who infects person B, C, and D. And this is about control measures such as test, trace, and isolate. So on top of thinking about when symptoms start, infections start, you've got to think about the timeline of when testing is starting, when someone's isolating, when a contact tracing is happening. And this just, the exact details of this particular one doesn't matter, but it brings in the ideas. This person A here is exposed, so that's the moment they get infected in this language. Pre-infectious period, so they're neither infectious nor symptomatic. Pre-symptomatic, so they're infectious but not symptomatic. The little thermometer indicates symptoms start. Then this person realizes they're ill, they self-isolate and report. So the grey indicates they're isolating, so they're less infectious, little red band there. Then they get tested and it can come back positive. And then you've got this tracing. So you've got this person who was infected during the pre-symptomatic period, who maybe gets pinged by test and trace. Then they've got a time to be traced, a time to be tested, a time to isolate, and that may stop onwards infections. And you can see all of these things and these processes are going to be very dependent on the exact time distributions of when these things happen. When someone's infectious, here it's modeled as symptoms are abrupt time of start, infectiousness is abrupt time of start. Of course, all these things are distributions, and understanding that is going to be really important to understand how you make test, trace, and isolate work, which factors are important. This gap from testing to results, how important is that? Should you just isolate with any symptoms, or is that taking us out, you know, for too much time? And of course, super topical. In UK, we've got a pingdemic where everyone's getting pinged, so you've been in contact with a case and isolating, and that's actually causing problems for our workforce at the moment. So lots of things to balance there. Generation time, key for this. Another reason why it matters, and this one's been of particular interest to me, is every week in UK, we have growth rates for England and the 4 nations, and they're presented as a R value, reproduction ratio, and also as a growth rate. And how are R and growth rates related to each other? Well, If you want to read about it, if you don't know already, we have a nice explainer in PLOS magazine written with Rachel Thomas and Marianne Freiberger. But cutting to the chase with the maths, if R is here, this is 1 over R, and the growth rate we're going to write as lambda, then they're related in this way. Right, in other words, it's a Laplace transform involving the generation time distribution. In fact, it's a Laplace transform of minus lambda, isn't it? There's an extra minus in there, an extra 1 over R. But the relationship between them is just this, which means how you translate between them depends on your assumption of the generation time distribution, its mean, variance, the shape of it. And an example of why that matter is, I think I've argued for a while that most fundamentally what we see in data is actually a growth rate. So these are cases for UK from last autumn plotted on a log scale. And when you plot it on a log scale, it's more crystal clear. You've got these long periods of, exponential growth, exponential decay. And it's that we're picking up, either explicitly looking at that and fitting a growth rate, or implicitly doing it by fitting a model of whatever complexity. I think the signal from reality is a growth rate rather than an R, even if people say it's built into the model. So whether you're explicitly transforming a growth rate or implicitly, because you've got a model, there is an assumption in there. And I get quite frustrated when someone says we don't need a generation time distribution because our model does it. It's like, well, no, you've got an assumption of one. This one here is assumed that it's exponential with minus nu. There are other models which assume not exponential, but it's a delta function, so that there's absolutely constant generation time implicitly in there. And people forget that. And it matters. It means your estimates for R can be all over the shop. So here's what happens with the estimate for R. So given a particular growth rate, you can translate this to a value of R based on your mean generation time in days. Contours here are a fixed growth rate. So for example, suppose I observe a growth rate that corresponds to this red line. What value of R do I infer? Well, it could be like 1.1-ish or 1.5-ish, depending on whether I think my mean generation time is 2 days or 8 days. So you can get a whole range. In fact, you get half of the real line if you've got a positive growth rate and correspond to any R greater than 0. If you put the appropriate generation time distribution in, you can't get a negative one you can't get R less than 1 for a growth rate, which is positive, that's bad. The only one which is unambiguous is flat, which must correspond to R equals 1. So you can get bad estimates. So the dangers with that are, say you've got a new growing variant, which we've seen a few times. If you ascribe all of its extra advantage in growth rates to being a value of R, or saying it's a higher transmission rate, you could have vastly overestimated its transmission rate. And overestimating R means you're thinking it's harder to control than it really is. So if you see a different growth rate, one of the things you've got to explore is, could it be a shorter generation time? All of this is true for growth. If it's decay, it's the other way around. If you assume a longer generation time than is reality, you always assume you're always going to falsely assume a more extreme, as in further away from 1 value of R. So there's that problem in there. And to drop it to a very particular problem with new variants that we faced in UK, April, May. So even if we assume that the generation time is the same between variants, and put aside that problem for a minute, if the generation time we assume for both of them is slightly wrong, then we're going to be misguessing the transmission advantage. So what we've got here is for one region of the UK, this is Northwest, which includes Bolton and regions where the Delta variant was not first detected, but first really established. This is actually S gene positive and negative. Rather than worry about that, so I can tell you that the red line is mostly picking up alpha, the old variant, and the green line by April, May is mainly picking up delta, the variant we've got now in the UK. And if you see growth rate for alpha was around minus 0.05, while at the same time growth rate for delta was plus 0.1. So what would you say does that mean for the R advantage for delta? If it's all transmission, how much more transmissible is it? Well, here's two plots based on just taking that snapshot there and there. Growth rate of one variant versus growth rate of another. If you assume a generation time with mean 4.2 days, standard deviation 4.9, and gamma distributed, you'd read off from here minus 0.05, plus 0.01. Growth rate advantage is about 80%. But if you'd assumed a longer generation time, you could be reading off easily, so 6 days, which is not bonkers, gives you a generation, gives you a growth advantage of plus 130%, which is stonking, right? It's saying we've got a big problem. We're going to have to, work twice as hard to lock down. So these are very different estimates. It all gets very crowded and squished, particularly up here at these sort of large ratios, where one's a bit negative, one's a bit positive, which is exactly what we saw with delta and alpha. This plot is taken from this paper, which is Rob Challen et al., which is currently on medRxiv. I don't think it's been quite published yet, but it's under revision. So a very real problem we faced. Okay, so hopefully that sold to you why we might want to care about generation time in terms of policy and control. And I'm sure this audience can think of many other reasons why we should care. Okay, so what shapes generation times or generation intervals? Tom, Britton, I agree with your comment. We need to decide what language you're using. I'm going to use times for the moment. And Kira introduced this really. I think there's 3 different levels involved here. And put them all up. They're all ordered by scale, if you like. So within host kinetics, what the virus is doing in that period of time between hosts, and also the local transmission opportunities, how the hosts are interacting with each other. And it's those 3 things together that shape it. And I don't think you can really understand generation times in practice without thinking to some extent about all 3 of these. And conversely, you can't answer it by thinking about one of these alone. Perhaps for many of us, the most instinctive thing to do is think about within host kinetics. I already, naturally mentioned, okay, maybe you have more virus and you're more infectious at certain points in your infection. It's a curve. I've realized this plot looks like someone presenting at a blackboard, but it's not. It's supposed to be a plot of observing sort of some magic stethoscope of what's happening inside that person, how much virus there is, what's going on with cells and the immune system. So virus infected cells, immune response. The virus between hosts, aerosol environment, personal protective, whether masks or not, and local transmission opportunities, mixing over short time. And I'm just going to present some bits to set the scene a little bit further on 2 of these, or at least the 2 that I know a little bit about. So we'll start off with the within host kinetics bit of it. So this area exists. It's been more important for chronic diseases, if I'm honest, like HIV dynamics within host. There is work out there for acute respiratory diseases such as influenza, and for COVID there's been a RAMP group in particular that's been looking at within host dynamics. The sort of thing that's thought about within host is rather than a population of people, you can see a population of cells. So target cell is one of your respiratory cells, still uninfected. It can become infected, it can die. Virus goes into the cells, virus is produced by the cell, you've got virus clearance, and this cartoon here doesn't even have the immune system, and you get these outputs. Just to show you some equations for a system like that. So again, I'm reverting to things I know. We looked at this 10 or so years ago, 11 years ago, in terms of actually it was influenza and actually it was horses. So Roberto Sainz was the first author here. This is the sort of system you get. It's fractionally more complicated than the cartoon, but it's the same kind of thing. You've got target cells. They can be exposed, but like humans, not yet shedding virus. So it's this period the virus is getting into the cell, doing its thing of hijacking the machinery, hasn't finished doing all that and destroying the cell and releasing virus. Meanwhile, we've got interferon, which is part of the innate immune system. The interferon can change the cells into this sort of waiting to become more impervious to virus, resistant, but they can get unlucky and get infected during that period as well. And infected cells produce interferon. You've got this nice feedback dynamics. This is just the innate immune system, not even thinking about the adaptive immune system yet. And in this paper, we did some fitting to observations from infections in horses. One of the, I mean, not saying population dynamics is easy by any means, but within host stuff is so hard for observing what's going on. You get these very indirect measures. These are very difficult and rare experiments to do to get a look at what's happening at the fine scale. In vitro work really doesn't capture the full thing of what's going on. It certainly doesn't. It's terrible for getting the adaptive immune system. So you're basing this on really indirect measures. So it's hard. In the maths, it's the same sort of maths as population level, but calibrating and building these models there's a reason this area is not so developed. It's hard. This is not just a cheeky self-citation, but there's a link back to our infectious disease dynamics previous Newton meeting, pre-pandemic, gosh, 7 or 8 years ago now. We had a huge meeting which was hugely important and influential in our area. And the outputs of that meeting, David referred to challenge papers being written now. Actually, we also wrote them back then. So we had a special issue of the journal Epidemics, which were all entitled End Challenges in blah, whatever the topic was. So this one was 7 challenges in modeling pathogen dynamics within host and across scales. And you can see my co-author here, Lorenzo Pellis, will be hearing from more tomorrow as well. So there's not so many answers in here, but lots of questions and challenges. So one approach of connecting the within to population level, and I'm showing this again just to show how crude it is, and it's not taking into account all the dynamics in between very well, is say this is your population level model. You've got DSDT. You've got your I, which depends on time, but also A is now time since start of infection. So you start building this sort of integral differential system for it. You can write this down, but somewhere in this, you've got to have this infectiousness at time A. This one, all the subscripts are because it's actually a multiple strain model that we put in here at the same time. And this beta term is the linkage. It's you use your within host models to generate these functions to go in here. So it's a nested model system. You have an output, which is all the things that beta can do, and you plug it into your population level model and hope for the best. This is one approach, but this one really is not calibrated for respiratory diseases. It was set up more for acute diseases, but it is still quite interesting for looking at viral evolution. Okay, so that's a snapshot of what I hope we're going to hear a lot more about and a lot more up to date and about COVID, about within host kinetics. I have no expertise whatsoever on this virus when between hosts, but the speaker after me is Kath Noakes, and I saw her pop up on video briefly. So I'm not going to be so silly as to give a bad introduction to this, but I'm going to say you're going to hear more about this from Kath very shortly. I do know about this bit. This is back to the epi scale. So I can give you some of the themes there that are important on the local transmission opportunities. And of course, back to my favorite non-pandemic, the BBC pandemic. This was a TV show first broadcast in 2018, but it's also a big citizen science project to understand better how people in the UK are actually mixing. And the reason for it is so we'd have better data and a better understanding ahead of a future pandemic, which at the time, honestly, I'm imagining will be 20 years down the line. BBC pandemic squad are all very much part of this, of course. there's two parts of the study, and I'm going to talk a tiny bit about the national level one, which had a lot of users collecting fairly basic personal data, location data, movement data. And I'm going to talk a little bit more about the Hazelmere side of it after that. On the national side, just to start to think about how complex people are, you know, we're not just moving by Brownian motion, we have complex lives. Here's an example of one person. Actually, it's not true. I've changed it so it's a little bit anonymized. We know to square kilometre where this person is once every hour for 24 hours. This person actually spends a lot of time here near Broxbourne. At a certain time in the morning, they go to this point here, probably to school. They spend several hours here and then spend an hour here, hour here, hour here, or at least at the moment it pinged on that hour they were there. So maybe a bit of travelling afterwards, shopping, seeing people, and then returning to this red square, which we can deduce as home. Got to think about their age, their gender, occupation. A 17-year-old at school, lives with 2 other people, and they will have reported who they're in contact with. So you also know their reported contacts as well as how they've moved. And also a little bit of travel survey there to act as a bit of a Rosetta Stone with some of the past studies. So people are complex. You can look at any one of these sort of snapshot slides for an individual in the study, and you can build up a picture of what their life was like that day. But also people are different between different days, right? So complex mixing. Age structure has been particularly important to us in this pandemic, and we might see things like this. The mean number of contacts of age group I, so I might be on this horizontal axis here, as reported by group J. Sorry, other way around. J is on the horizontal axis, so 20 to 24-year-olds will report a lot of interactions with 20 to 24-year-olds. And you can see there's a higher up band, which is a generation above, a lower down band, which is children, and there's a very splurge here of working age and strongest age assortativity in the youngest age groups. So you've got these sort of patterns as well. But I do want to talk about the Hazelmere dynamics because it brings into play the really fine temporal structure as well, which becomes important when we're thinking about generation times and the scale of 2, 3, 4, 5 days over generation times for COVID. So here we had 468 users and a 469th patient 0, who we will not very anonymously call Hannah Fry. And it's data over 3 days, and it was much more detailed relative location data. It was actually much more intrusive. And we're always very grateful to these people in Hazelmere who took part in this. This was a very, very trusting thing to do, and it was very useful. So 3 days, really frequent recordings. Rather than just being snapped to that 1 kilometre grid, it was accurate as GPS would let us be. And it was a really detailed study of one town. What does community epidemic in detail look like? There's Hazelmere there, sorry. London is there. This is Southeast England. Portsmouth is there. So it's sort of halfway between London and Portsmouth in some sense. Well, it's on the train line in between, or the main motorway in between. Always very close to my heart. I was born here in Crawley. Right. This was the movie produced for the TV program, just to really illustrate this. I find this really useful. So you can focus just on the left if you wish, but on the right as if we vaccinated some of the super spreaders. Not much happens for a bit. These are the people just moving around. In fact, can I fast forward it? Oh no, purple dot is Hannah coming in. She goes to a yoga class, she goes to a bookshop, she goes into a hardware shop, and she infects people. We've rigged the parameters so infection, the exposed period and then infectious period happens over the period of hours to make it fit into the narrative of 3 days. So this is not quite flu, this is too fast. And you can see the purple dots may cluster for a bit and then they jump across town as they go home, or there's a whacking great supermarket here that Hannah goes to, and then there's a pub. And people go mix there and then return home and then can infect their households. And this is day 1, this is now getting to the evening. And this dynamic changes over the days. our days were Thursday, Friday, Saturday, so the weekend looks different to Thursday and Friday. And again, this matters over the course of a generation time distribution. This is just extracted from the mixing data, so it doesn't involve our model at all. This is figure 1 from Kistler et al. The nodes are our Hazelmere people. The node area, there's some big ones and some small ones, is proportional to how many different other people they met over 3 days. And we put a line between people if they were in contact, as in they were within a certain number of meters during part of a quarter day. And it's 3 days. So someone, if they're in contact with them the full time, there's 1 pair up there. You just get all the lines. From this, you can pick out various structures, such as people who are probably in the same households. You can see, okay, so this is household here. This person's in contact with some of them for some of the time, so maybe visited. It's a real mess in the middle to plot, but there's all kinds of fine scale structure in there. You know, we're not random chickens mixing. There's lots of structure. And again, this will interact with environment as well, whether at home, whether at school, whether at a supermarket, or just walking past in the street, which will interact with this environmental and aerosol scale. So it's fun. There's a lot going on. If this plays, you can, thinking about it as a network is not quite right. It's really a very, very dynamic network of how we mix. This is a snapshot for 15 minutes. This is the integral over an hour. This is integral over a day. And this is over all time. But you've got these recurrent structures. This is just picking 50 users or so. I should say that the full data set is in that Kistler et al. Paper. At least the data set of how close people are to each other. We've taken out age, gender, everything, because it was too unanonymized otherwise. But you could reconstruct this plot from that paper. Oh, stop watching it, it's too interesting. And if I can sneak into this warm-up act overview, there's a specific challenge. Given complete relative position data, and I tell you exactly what my spatial model is and the parameters, can you tell me who to best vaccinate? And if the network was not dynamic, I think this is a really doable problem. We know how to address that, but when it's a dynamic network, it's really not so obvious. So this is looking at no vaccination, random vaccination, various more clever strategies, and the final size. Which 47 people would you vaccinate out of the 469 to bring things down the most? And can you come up with a general method given a dynamic network? Still open problem. It's all still there if you want to have a go at it. Anyway, right, having solved hopefully a problem to someone, come back to, I hope I've introduced to you what generation time is, at least a basic language for it. Maybe subsequent speakers will challenge that and reshape it, I hope so. Why we might care, and again, I hope subsequent talks will introduce other ideas on why we might care about this, and crucially, the things that shape the generation time. Now, for me, this meeting is important in itself for understanding the generation time better, because it matters for so much we're doing. But if I'm honest, the even more exciting bit is getting these 3 scales linked together, and those of us with expertise in different bits of this talking together. This is the valuable thing. This is a key problem I think we can make some progress on, but I think there are others out there, and thinking about other key questions at the moment, understanding waning immunity, what's happening with that, is also a little bit of what goes on in between hosts here and within host, and viral evolution stories, I think, also cut across these scales at the moment. So yeah, if there are interesting tangents, it's okay to talk about those as well, particularly if we can save them up for the more workshop day on Friday, which I hope many of you can come to. There are no stupid questions. When we're talking between fields, we've got to be willing to be open and asking questions, and speakers, please, you know, give us the basic introductions as well. Don't, you know, bring us all on board with all the ideas here. We're all struggling on one or other bit. But yeah, I'm really looking forward to these talks and further discussions in this meeting to bring all these perspectives together. Looking forward to it. Thank you.
Great, thank you, Julia. That was a really great overview to kick us off for the next few days. So there's some questions that have come in from some people from the audience, so I'll get straight to it. So Chris Illingworth says that some studies, so for example, he et al. In Nature Medicine 2020, have described cases for which there is very strong epidemiological evidence of direct transmission, then have fitted a simple statistical model to symptom onset dates from these individuals. To what extent is this kind of approach sufficient for identifying what is the generation time?
I can't fully answer that, Chris, and I think you're going to get a more expert answer, I think, later in the schedule. I don't know if Will Hart, you'll be addressing some of this, but some of the problems there, particularly with the early studies, is you don't actually know who the infector-infectee pair is. You're assuming it, and then you're looking at not actually the generation time, but maybe what you're seeing is the serial interval, the time between symptoms onset and symptoms onset. And there are lots of fantastic statisticians on here will tell you that can give you all kinds of biased estimates, right? And you've also got a problem that it's also intertangled with who you think the infector-infectee is as well. So the Her et al. Study was really, really, really important early in this pandemic, but it's deeply imperfect as well. And I'm sure the authors would say that as well.
So the other question is sort of related to that. So they say, thank you for a very interesting talk. May I ask you, what can we do to estimate the generation time, except collecting the empirical data, which possibly indicates the time of infection? Also, are there any required considerations when we estimate the generation time from the empirical data?
Thank you for the question. It's very, very linked to the previous question. When you're observing people with their symptoms onset and inferring the pairs, you've got all those problems. However, thinking about the three scales, you might be able to make observations that get at various bits of these. For example, if you look at the host level, you can look at CT values, i.e. how virusy someone is, but how you translate that to how infectious they are is certainly for flu, we've never got to the bottom of that. So for COVID, good luck with that. And then how that translates to how infectious someone is in context with their environment and their mixing. Well, that's what we can think about in this workshop. So rather than just measuring it, well, measuring it is hard, but thinking about what shapes it by looking at it from the modelling point of view, I think is what we can get at here. But fab questions, sorry, I can't answer better, but that just highlights why this matters.
Yeah, and just sort of following on from that, Julia, I guess coming back to why it's important to try and understand a bit more about this generation time in the context of new variants. So I guess one of the challenges could be when you're estimating the generation time, because I think that study was initially from the very beginning of the pandemic, and then obviously you've got, you know, a huge evolution in the way COVID has, the virus has evolved over the pandemic. So it then becomes difficult because you can't really estimate it because then you'd have to estimate it every single time, right, as it's going forward. Whereas if we understood a bit more the mechanics, is that kind of what you're hoping maybe to get out from this meeting?
The generation time is changing the whole time. First, it's shaped by the variant, and there's some mutterings, and maybe we can go beyond the mutterings in this meeting, that Delta has a shorter generation time. You can only look at that indirectly by looking at virus shedding curves and saying, well, kicks off a little bit earlier, and explore that. But the other problem with the early studies is it's very contextual. The generation time, it's not that purely within host, you're infectious these days and you're not others. It's when are you mixing with others? If you're the generation time when we're in lockdown, mixing with our households, potentially is very different to the generation time when we're fully unlocked and behaving more normally, right? Because it's a function of that mixing as well. And it's a function of what's happening. You know, maybe you're shedding differently from the nose and the mouth. So if you have masks or screens, that can change the generation time as well. So everything can happen, basically.
So there's another question coming from, oh, is that from Tom? Oh, it's okay, Tom. I'll put the I'll put it in the chat because it came through on the question, so we've got it, the reference for the study that I mentioned, that Chris Illingworth mentioned. So I guess just one last question, if I may, Julia, before I pass on to Kath, would be, what do you think? I mean, so obviously people haven't done that much before trying to link up these scales. So what do you see as potentially some of the challenges?
It's talking across disciplines, I think, and that's the key reason why it hasn't been done more. Each of the scales is hard on its own, and the fields are rapidly changing on their own. No one's an expert in all of these things, but I'm really hopeful getting the right people here with the curiosity about the different areas here, thinking of a focus problem, you know, we might get somewhere. But I do think it's because it's cross-disciplinary, and if you're thinking about one level on its own, you're not getting the full story. So we're getting this sort of, you know, we're seeing different bits of the elephant, as it were. But hopefully together we can get a bit further, or at least start the dialogue. Every instinct is getting these different levels talking, as there are nice problems that we will be able to tackle, and productive, interesting things will happen. At very worst, it'll be really interesting.
There is actually just one last question that's come in on the chat, which I think we have got a bit of time because we're running a bit ahead of schedule. So Juan asks, the generation time is a biological measure given a strain of a pathogen likely to stray within a narrow threshold across human populations. Would it make sense to use an average value across all models and then parameterize contact rates?
Ooh. Okay, so you can do stuff by merging studies between populations, but as mentioned, potentially the generation time could be contextual, both by population and what's happening with that population. You've also got the generation time, you know, from child to child could be different to adult, etc. So everything there. Let me try and understand your question further. Would it make sense to use average values across models? Sometimes, yes, because you just get more power by doing things, but there's a world of detail there, and sometimes it's not going to be appropriate, but it's going to depend on what you're doing, I think.
Great, thank you very much, Julia.